Programming Throwdown, episode 165, Differential Equations. Take it away, Jason.
Hey, everybody. This is going to be a cool show. We're going to talk about something that Patrick and I are definitely not experts in, but I've had to do a lot of it recently, and I think it's very important. And so we're going to talk about DiffEq.
Oh, man, you already shortened it. I'm already out.
I don't know if... did we have to take DiffEq in college?
I did.
Was it a requirement?
It was a requirement. I did very, very bad at it.
I honestly don't even remember taking it. So that goes to show something right there. I don't know if I took it or not, but we are going to dive deep into it. It turns out it is really important. And so we'll get to that. But before we do, I want to talk about spreadsheets. I actually fell back in love with Excel, in this case, Google Sheets. But we really take it for granted. I mean, sometimes we even make fun of people who, do tons of things in Excel. We say we could have done so much of this in Python or R or what have you. But, one of the really powerful things in Excel is the sort of recursive nature of it and how you can kind of incrementally build on top of some data, and you can see all the intermediate values as long as you don't make the functions too complicated. So I had this thing where it's actually it's pretty nerdy, but there's this video game called X4, and in X4 it's one of these grand strategy games. So you mine ore, use ore to make solar arrays, and solar arrays give you energy, and you can use the energy in the ore to make spaceships, and anyway, it goes on forever. And I thought someone posted a Google sheet of all the different resources and some stats on them. And for the resources that require you to build things like solar arrays, what are the ingredients? Okay, so I had this Google sheet, has material, the cost to acquire it if it's some raw material, or if it's not a raw material, the time to build it, and then all the requirements, inputs, right?
Yep.
And so using some Excel functions, I was able to recursively figure out the time it takes, the total time it takes to get any ingredient.
Oh, wow.
So it's the time it takes to build that thing plus the time it takes to build all of its components, times however many of those you need. So a solar array, it takes 60 seconds. That's your base time. Plus, it needs 10 of this other product. So whatever the total cumulative time is of that other product times 10 plus this, right? And so that other product depends on other products. And so it's this recursive thing, but, because I just specify, and we talked about recursion in a couple of shows ago. What's a pretty good tie-in? So because I just put this recursive step in, and then I just control dragged, that equation onto every row, and Excel instantly figured it all out and said, oh, for you to build, medium-sized battle cruiser, it actually takes 18,000 seconds or something, including all the other things you have to build.
And then you cried because you had already done it twice.
Yeah, I mean, it was so, what it made me think about is that's really cool. I just specified this simple recursive step, and then Excel, handles not calling the function too many times and caching the values. It kind of did all of it for me. And I wonder if a Python library that does something like that would be really useful, some extension to NumPy or something, where in certain values in the array you could put equations, and then Python would just do what Excel does. It would just figure it all out for you.
Yeah, I ran into something not as complex as what you were doing, but we were talking about index investing a bit 2 episodes ago again. Oh man, look at us tying it in. Good us.
Yeah, look at this.
But I had this thing where, some time goes by and then you want to put some more money in, but you want to rebalance what's there, right? So the idea of rebalancing is you have some target. I want the most common, one that gets toted about is 60% stock and 40% bonds, go read up on that. I'm not actually advising you to do that, but
Yep.
let's say you want to do that. So you have some index that is your stock allocation and some that is your bond. And let's just say you have two for simplicity. Then over time, one goes up and one goes down, or both go up, and you want to get back to your 60-40 target. But you also want to bring in some new money. So could you run this on a calculator for two? Yeah, it's really not that bad. But it's just dropping them in this case, I think Excel has extensions to do it, but I was doing it in the Google version, Google Sheets. And they have go get the latest stock price. So as long as if I updated it each time I do it, then it knows how many shares I have. So it'll tell me the new price. I say how much money I want to put in, and then it basically calculates my trades for me. And if I want to, for instance, like disallow selling, like I don't want to sell something, I just want to buy new, then, you can do that with the conditional logic and sort of like you're saying, iterate back on it and sort of, step on it. Do not necessarily even iterations, but just one column to the next where you're sort of rolling forward your computations. And it was just like, because it turns out it wasn't doing it with two, I was doing it with like five different indexes. And so, it was just so much nicer to like set it up once and then be able to just rerun it. If I had sat down in Python, I know there's an API for pulling down stock prices. I know I could have put my stuff in a CSV or a JSON and read it in and done it. But I'm not clear that I wanted additional flexibility. I'm not trying to solve this for every person or every case. This isn't my job. I just wanted a quick solution. But I will agree with you that my hobby horses on this are people don't want to learn SQL, and we talked about that before on the show. But I think people don't like to learn spreadsheets. There's a group of people who just don't know how to run Excel or Sheets, and they don't know how to get graphs really easily. And they say, it's okay, I do it in Python. It's like, but I sort of guarantee if you only made me make this chart once or only for one thing, doing it first in the spreadsheet. And then if you go to do it again, fine, I'll give it to you that the second time you have to do it, you can do it in Python. But that first time, you almost guaranteed if you know what you're doing, you're going to get it faster in the spreadsheet, just dumping out some output, new line separated dump from your program. And then you can copy paste that into Excel and get your plot much, much, much quicker.
Yep. Yeah, totally. And in your case, you're talking about balancing. So, if you had a certain allocation, a certain state, then like how much of something to buy or sell to get you to equilibrium, right?
Mm-hmm.
So you have actually a differential equation.
Oh, no.
You have an equation that says, here's how I get from where I am to where I want to be. But then if you take a really large step there, you might end up buying like way too many bonds and then you're unstable or something.
Okay. Well, before we get into that, we will, 2 episodes ago in our duo, we were talking about the buzz and excitement of LK99.
Yeah.
And it feels like what is the meme? It's back and then it's over and it's back. And if you followed it on X, I'm just going to go with Twitter. If you followed it on Twitter at all, you saw these memes go by. But it seems that a lot of people who sort of bided their time and really thought through it and did some analysis are pretty convinced that at least at this point, there's no evidence yet that LK99 is a superconductor. So there's a Nature article now out sort of saying this, and some sort of more well-reviewed stuff is out. People are that the aftermath is somewhat interesting. There's still some studying to be done of the material, which happened. But then it's very divisive. I'm not a academic scientist by trade, or even a scientist, period, I guess. But there seems to be a big divide between, was this a okay thing that it happened this way? The original article was a preprint, right? So it wasn't actually in a peer-reviewed journal. It was just a preprint that everyone got excited about. Was this a waste of resources? And, does someone lose reputation? Or is this is just a more open, involved, broader scientific community and hobbyist sort of thing? I'll say from the sidelines, that's the most excitement I had about material science in a preprint article ever. Yep. I learned a lot. Clearly, there was a lot of speculation going on that we talked about a little last time. People saying things that just weren't going to happen or weren't true, even if it had been everything it promised. But yeah, so what? Like, I don't personally see what was harmed if people decided to try to pursue replicating this using resources that they otherwise shouldn't have. I feel like that's a game theoretical decision that they made, and it's sort of case by case. So I don't sort of hold the broader community, but again, not my my domain. So it's possible that I'm missing some part of the equation there.
Yeah, I mean, I think that it's a good question. I have a couple of things here. One is I've seen some people say that okay, it's not a superconductor, but it's still important because it's like a better conductor, and there's certain things that we learned because of it. And so it seems like it is some kind of incremental step forward. The other part of it is, there's definitely like a outrage economy, and so I think on things like Twitter, um, like a lot of people probably got a lot of followers for being, really passionate and about it, and so that's a really big problem. I think that it's hard to overcome. Do you know if they're still like, is that material useful, even if it's not a superconductor?
Uh, yeah, I think some people think it might be interesting, but I once the hubbub has sort of died, I think a lot of people became a little more soft spoken about things. And
Yeah, right.
it's like anything, once it becomes more subtle, right? It's a little harder for people outside to maybe understand the implications. I expect people will still continue some amount of studying down this avenue. It seems like there's some novel properties, but yeah, I think the unlock of a actual room temperature, and to be clear, it's room temperature and room pressure, like sort of normal atmospheric pressure.
Right.
The two thing missing either one of those sort of makes it just not the step function of new discovery. So even if it is still a superconductor at low temperature, which isn't clear, that like it could be a massive improvement, but not getting to where we are, where the speculation was going, it's sort of a letdown. And maybe that's where people are pointing out, is because it's a letdown of the public, then the public loses faith in the process.
Yeah, that makes sense. My article is on normalizing flows. Have you ever heard of this?
I know these words individually in many contexts, but I do not know what this is about.
All right, so I'll explain. So, we have, in random math, right? We have probability density functions, right? And so what this means is, if you look at like a coin has heads or tails, right? And so it has a 50-50 chance if it's a fair coin of being heads or tails. If you look at a die, a die has 1 through 6 printed on it. And when you roll it, if it's a fair die, you have an equal chance of getting 1 through 6, right? Well, how do you do this with random numbers? And so with random numbers, you do it through probability density functions, which are like actually really non-intuitive. Maybe like a good example is like voltage coming into your house. So, you have this voltmeter and it measures the voltage, a multimeter, and it measures the voltage coming into your house, and it says 120. But it's not like exactly 120 or like exactly this number of electrons past the multimeter. It's some kind of rolling average of some, estimate. And so if you were to like dive into the multimeter, it's probably getting 119, 121, and these are going to be floating point numbers like 119.x, 120.y, right? And then it's averaging them out and saying 120. And so what you really have in your house, the voltage in your house is going to be some density function where the mean is 120, and then it has some tails. Like sometimes when you read it, you get numbers that are greater or less than 120, right? Does that make sense?
Yep.
Okay. So it turns out, if you have an expected value and there's just some error on either side, a normal distribution does a pretty good job, and those are pretty easy to calculate, right? What if you have a really weird thing? Like, for example, what if I have a data set that has American voltage data and European voltage data in the same data set? So, like, half the numbers seem to be around 120, but then half the numbers seem to be around 230, and they're all just mixed together, right? So if you just fit a normal distribution to that, it's gonna tell you, oh, like almost all your voltages are around like 180 or something, plus or minus some error, which is not really representing what you have. What you actually have is what's called a bimodal distribution, where you have one mode. You have one cluster around 120, and then you have another cluster around 230. So, what you want to do is you want to know the distribution of these kinds of data sets, right? These complicated data sets. And once you have the distribution, there's all sorts of interesting things you could do. Like, for example, if you know the distribution of the voltage in your house, and let's say it's 120 plus or minus 1 volt, right? Then if the voltage is like 130 or 150, like, oh, my house is really messed up. Like my electronics are going to start blowing up. I need to do something about it, right? But if you measure the voltage in your house and it's like 120 plus or minus 20 volts and everything in your house is still working, then like, okay, I have a pretty good tolerance for voltage in my house, right? And so when you get to these really weird distributions, you still want to know the same thing, which is like, have I seen something like this before? And so to answer, have I seen something like this before questions, you need to have a density function. Like, how dense is this part of the system? How dense is this function? And so normalizing flows are a way to get like almost arbitrarily complex density functions. So if you have really weird shapes that are that you can't really categorize as with any normal density function, you could always run normalizing flows, and it'll learn that function for you. And so it's a bunch of really cool things you can do with something like this. Like, I'll give you an example. There's these like breast cancer data sets, right? And they're pretty famous. They came out of UC Irvine, and it's basically a whole bunch of data of like stats on people, and then I think there's maybe pictures, mammogram pictures, and then there's like whether there's a tumor or not. And you could train a classifier and say like yes, breast cancer, or no, breast cancer, and there's a bunch of tutorials on how to do this on the internet. But you could use something like normalizing flows to say like, have I seen a candidate like this before? And if the answer is no, then maybe you don't trust, the screening as much. So if the screening says cancer, but you've never really seen anyone like this who had all these qualities, then maybe you ran an additional test. But if it says cancer and you've seen like tons of people just like this and they were all cancer, then you're much more like certain, right? And so there's a whole rabbit hole there, but check out the link. It has a really good explanation of how to do this. And this is a relatively recent thing. I mean, it used to be that you would take that normal distribution, the one I explained before, and you would do what's called mixtures. And so mixtures are good if, like the example I gave, where something's either 120 or 230. So if you had something that was either like one of several values, just with some error, then that's fine. But if something's just like arbitrarily distributed, like it's just like some weird shape, there's not really any way to recover that until some of these recent methods. So I've been keeping an eye on it, and they've been making tons of progress. This isn't even the latest one. It's just the one that I found the best explanation for. That's relatively modern, but I think that there's going to be a good future to these methods.
Yeah, this is interesting. I naively would have thought, I have come across this problem before. I didn't know this was done this way. And what I did is sort of, if you think about histogramming and then just taking the data you do have and sort of making, I guess you would almost call it a discrete density function, and just using the data you do have to estimate the percentages, which of course is difficult for things that once you've done the histogramming, like things that come in between, right? But yeah, there's some balance there, but that's actually really interesting.
Yeah, I mean, if you've ever built a heat map, I mean, that's basically a density function. And so this kind of takes it to the continuous space.
Very cool. So my next one is probably going to require a bit of explanation, but it's how is llama.cpp possible? So llama is, and Jason, you're going to have to help me if I get the background here wrong, but llama is one of the sort of ChatGPT equivalents that came out of Facebook. And importantly, Facebook released the parameter weights as well as the architecture. And they just recently announced Llama 2. And there's sort of a debate around, is it open source? Is it not open source? They have some wording. Go read the contract yourself. The answer is, for most people that aren't like a already established big company, you can pretty much do whatever you want with it. And there has been a group of people who had come out with this tool, llama.cpp, which is basically implementing without, I don't actually know, I guess Llama is in probably PyTorch or something similar, but without any of those frameworks, from just sort of bare metal C++, implementing all of the required tensor operations and things that you need to do to take the weights and to take inputs and to get the expected outputs. And the reason this is really interesting is, if you follow the space at all, the expectation of running Llama is that you do it on either some specific tensor hardware, like a TPU or whatever, or more commonly on a very now expensive, from a series of sort of circumstances, very expensive GPUs. And the biggest thing is you want to think about transferring the model weights to the GPU's memory, and then it allows all these operations to take part very, very, very quickly. And this article sort of goes into this explanation that this is mostly about memory bandwidth, right? So the GPU has very expensive, very high bandwidth memory, as well as discrete parallel processing units for doing all of the operations needed. Llama CPP doesn't benefit from sort of all of that GPU work. What they are trying to do is using SIMD operations. So it'd be like SSE, Neon, AVX, these kinds of things, which allow you to use your CPU's parallelization, but also using the quantized models. So instead of floating point or double parameter weights, they do some retraining for a lot of these to get them down to 4 bits or 8 bits per parameter. And these have billions of parameters. I think most of them are like sort of like 12 billion parameters, right? So you're talking about a huge reduction in the amount of memory, and then running them on just basically your CPU. Now, albeit a sort of accelerated thing, but the nice thing is you normally have a lot more memory in your system, RAM, just normal sort of like DDR4 RAM or whatever, tied to your main CPU than you do on your GPU. So most people would not be surprised to hear 32 gigabytes or 64 gigabytes or even more of system RAM. But GPU RAM, you're probably 24 gigabytes would be really big. Even 12 gigabytes is sort of large. And so a lot of people don't have a GPUs big enough to do this, but they do have CPUs. And so if you're willing to lose some performance due to the quantization, although not as much as I was expecting. When you say, I'm going to use 4 bits per parameter, I assumed, oh, this thing's going to be just degenerate, but that's not true. It actually retains a lot of its functionality, which is fascinating.
Yeah,
but
definitely.
Then also, then you can do it on your CPU. And the token speed, sort of the amount of tokenization that occurs, is still, kind of low, only like maybe 1 per second or that kind of thing. So not enough for sort of like that interactive chat feeling exactly, but also not bad for not having to go out and buy, $1,000 GPU and power supplies and everything to go with it.
Yeah, this is amazing. Super exciting. I think it's really cool. There's a ton of posts about this, and yeah, the 4-bit quantization is pretty impressive. I thought that with just 16 numbers to represent each weight, that you would have lost something really important. But
sure.
But yeah, it works really well. I actually have, with the 4-bit quantization, I have a Llama with 7 billion parameters that runs real time on my phone.
Oh, yeah, that's cool.
Yeah, there's an app called MLC Chat. This is for Android. I'm not sure if they have it for iOS. But you can run MLC, you can install MLC Chat, and then you get a 7 billion parameter model right there on your phone. It doesn't go to the internet or anything. It's pretty remarkable. And it will definitely hallucinate. I asked it what was the capital of Sri Lanka, and it made up a town. It might be another town, but it's not the capital. So it'll definitely hallucinate. You have to be careful. But I asked it how much Pittsburgh Pirates baseball tickets cost, and it nailed it. So, I mean, these are pretty esoteric questions. You basically have the power of, a Google on mushrooms on your phone. And so it's pretty amazing.
The thing that's interesting, I guess, is if someone was having this debate, like, oh, if you're going to be stranded on a desert island, is it better would you take a USB stick with, this is a terrible question, but USB stick for survival of like ChatGPT and what it knows and doesn't know, or a compressed Wikipedia?
Oh, interesting. Probably ChatGPT, right? What do you think?
I don't, I mean, right now, probably Wikipedia. But given like, if we sort of assume things continue to improve, I think that might start to change, which
Well,
is,
actually,
oops,
yeah,
go ahead.
the Wikipedia one, would you get a search engine too, or do you have to like?
I think so. I think yeah,
Oh,
you could
okay,
get a
that's
search
kind of a
engine.
game
Yeah.
changer. Okay, yes, I'd probably go Wikipedia.
But I think the interesting thing is Chat GPT would potentially know how to surface in a more interactive, queryable manner, or even distill something. So, you're talking about normalizing flows, right? And some stuff. If I had questions about this, going to Wikipedia might quickly go over my head, and it's going to take me a very, very, very long time to get to where I need to be to understand. Versus, Chat GPT could synthesize that down for me and potentially explain it. The problem, like you mentioned, is right now it's sort of not self-aware of when it's hallucinating, and so you could potentially end up getting an answer that it's very confident but very wrong.
Yeah,
I also
yeah.
don't know if you described something, right? Like if I described a coconut to ChatGPT, maybe it would be able to tell me it's a coconut. It would be very difficult to query Wikipedia for finding out, what is this thing I found on my desert island and can I eat it?
Yeah, I mean, I was thinking about um, building a device like this. My idea was basically a flashlight that had an open source large language model and speech to text and text to speech. So it's like you could hold the record button and say, is this tree with 4 leaves poison ivy? And then it would say something back to you.
That is really cool. Although you could also use it to start a fire with the heat it generates. So you kind of like perform two roles.
Oh man. Um, all right. So actually, my news is also related to LLMs. It's this cool website called chat.lmsys.org. And you can go there, you can ask questions to a variety of different open source large language models, and you can even ask questions to multiple at a time and see what the different answers are like in the spectrum there. So I typed in to the 13 billion Llama 2 model, what are normalizing flows? And it nailed it. It said normalizing flows are a type of generative model. They use a series of invertible transformations to model the distribution of the data, and it went into the different types of flows. Um, it doesn't talk about radial flows, which are the most popular. So it missed out. It listed 4 flows, but in my opinion, missed out on the most important flow. Um, so in general, I think that that's kind of in line with what you'd expect. Where like some of the details are kind of hazy, but it gets the overall idea right. Um, Yeah, I mean, this thing nailed it. It explains why it needs to be invertible. Really impressive. So yeah, check this out. If you haven't really been able to access open source models, it seemed like it's kind of too far from reach technically. This is a super easy website. You literally just click, and it's basically the Chat GPT interface, but for open source models. And so, you can play around with this. It's using someone else's compute, so it's totally free. Maybe at some point you'll get rate limited. I haven't tried that, haven't gotten there yet, um, but you can just play around with this, and if it solves something for you, then you could that could justify taking the time and energy to get one of these running on your own computer. Also, this LM sys is all open source, so you can actually clone this repository and make your own version of this, where on your computer you can ask yourself questions or your hardware questions. So you could go from this ChatGPT interface to something running on your own hardware, which is pretty exciting. Um, I've talked to folks who are generating real value with ChatGPT. Um, ChatGPT is so cheap; it's really hard to justify, the open source models. A lot of the folks I talk to are just using ChatGPT. My interactive fiction game, I have a bunch of folks playing it, which is really cool. And even with all the folks playing it, last month my bill was 57 cents. So it's hard to compete with that. Um, but yeah, I mean, I think for sensitive things or as a curiosity or for whatever reason, if you want to do the open source ones, this is a great opportunity to see how they compare and how they've been maturing.
Time for book of the show.
What is your book of the show, Patrick?
My book of the show is is adequate for my level of thinking. Math with Bad Drawings by Ben Orlin. So I have not dug all the way into this book. I have this book, and I am familiar with some of the writing here, and I've read a little bit of it. But for me, having I'm not a mathematician by background or by training. In fact, I did very poorly at it. Spoiler alert for the upcoming topic. But I will say that I do end up having to do a fair bit of math, as I think many people in computer science end up at one point or another, or I guess maybe depending on your sort of role. But I do a fair bit of math. But for me, it has to make sense to me, and it's useful to find people who, at minimum, find alternative ways of explaining. But I will say find non-academic ways of explaining intuition behind things. It is sometimes hard to sort of explain arbitrary topics via intuition from start to finish. But there's a number of people I'm very happy to have found. And we talk about one later, but there's 3 Blue, 1 Brown is like a YouTube channel we've talked about before, where he does these math explanations. Even watching just math videos on YouTube in general that aren't classes are good. But Ben Orlin has written this book and sort of covers a variety of topics. There's several follow-ons in the same thing. One about playing games, one about calculus, and just sort of some comic just to kind of keep you engaged, but also just sort of cheesy illustrations in order to sort of help you think about it. And it just vibrates sometimes with how I think about the world. And so I recommend this book if you're at all curious, if you're a math tourist, I would say, who's just interested in kind of a light treatment, a popular treatment, I guess, of a lot of these topics. Definitely check it out.
Very cool. Actually, you sold me on it. I literally just bought it while you were talking.
Oh no, it's gonna be book of the show next time for Jason.
It's gonna be my book of the show. We were talking about this before the show. How sometimes a lot of the book I'm reading right now is kind of invalidated because it was Patrick's book of the show 7 years ago or something. But doesn't mean you shouldn't read it. Definitely go back and read all of our books of the show. A lot of them are real winners. All right, my book of the show is beyond reading Brandon Sanderson, which we talked about a couple episodes ago. I was playing this text adventure called Overboard. It's from the people who made 80 Days, which was my book of the show in 2017. This one is interesting. The challenge with interactive fiction is replayability, right? I mean, clearly, a book has, very little replayability compared to video games, a regular book. And so interactive fiction, you have to kind of figure out, if you have to create all this content for all these things a person could do, but then they only do one path and then leave it, then a lot of that content is might not be explored by most people. So they want you to be able to play the game multiple times. And this one takes an interesting approach where they have a system of achievements. So, you play the same game every time. There are multiple endings, but a lot of the same thing happens. It's deterministic. So if you do the same thing at the same point in time, you'll end up with exactly the same ending. But as a way to keep you finding new content, they have this system of achievements, and the achievements are based on what you have and haven't seen. So if you play the game and just coincidentally you get the best possible ending, then you'll get an achievement for kill as many people as possible. Be like the most evil person possible because you haven't tried that yet. I thought that was really, really clever. I feel like it wasn't executed perfectly because it's not clear how to get some of these achievements. So you see the achievement and maybe you play, you don't get the achievement, you have to keep trying and trying. And while you're trying, you're just trying to do random things. It didn't do the best job of keeping track of what you've ever done in the past. So it has some work to do there on execution, but I love the idea. I think this idea of achievements kind of takes interactive fiction and makes it more like a roguelike where you start the game with like advantages the more time you play it. So I think there's something really powerful there on the game design front, and I had a lot of fun. It's a good story, and so let me just check really quickly what it costs. I can't see what it costs because I already own it.
Right here,
but
I'm gonna help you out.
yeah, ZV to build. Yeah, it's probably like $5. Totally worth it. Highly recommend it. $6.49. Definitely, it's worth it. You'll easily get a few hours of entertainment minimum out of it. So. And if you don't want to buy that game, you can actually buying that game doesn't support us because it's not an Amazon book. But if you don't want to buy the Math with Bad Drawings book like I just did, you can also support us on Patreon. So if you go to patreon.com/programming throwdown, big shout out to our supporters. We have had an influx of supporters, which is really cool. I wonder if that's companies forcing people back in the office has something to do with that. I don't know. If you are forced back into the office and that caused you to support us on Patreon, we lament the fact that you were forced to go back in, but we really do appreciate the support. All of that money goes in an account which we use for the show. We don't really pocket. We don't actually literally don't pocket any of it. We use it to try to bring more people into the show and spread the word. So we really appreciate every dollar of support that we get there. And with that, we'll go. Oh, go ahead, Patrick.
Oh no, just saying thanks. You go ahead.
Oh yeah, thanks everyone out there. And we'll go to tool of the show. Why don't you go first?
Okay. Mine is a website, FF Improviser. Good luck trying to Google that. You could just check the show notes. But this is, that's not even the full website. This is a GitHub link to a sort of interactive website with, I guess what you call it, almost FFmpeg one-liners. So I've had FFmpeg as my tool of the show before. Jason did, one of us did. Super powerful tool. Horrible command line interface. I'm sure it has to be.
Definitely.
It probably has to be. I'm not saying I could do better. To be clear, please don't at me. Well, good luck. You can at me. I don't see them.
Yeah, you don't have an
I don't even know where you would at me at. But anyways, the benefits. Okay, sorry. You can send me a letter if you could. No, don't send me.
Yeah.
All right. So FF Improviser has a bunch of things you may want to do with FFmpeg, and then gives you sort of one-liners that you can use to combine together. And so definitely makes a very powerful tool, but hard to use, a little easier to use, helpful. So definitely check it out. I also am bumping into this. I did see recommendations for a group of similar tools, including some like visual. If you ever played with like LabVIEW, like you drop little modules in on like a data flow graph and it'll sort of generate FFmpeg commands for you. So shout out to a bunch of people like out there trying to make ways of FFmpeg easier to use, because it's truly a powerful tool. I mean, it's used all over the place. This is really awesome. Video and video codecs are insane. I still like don't even profess to understand what any of them do or are, or the difference between container versus I'm not even going to say it. Anyways, so definitely check it out. FFmpeg Improviser, FF Improviser. Very useful tool for helping you, because if you're like me, never remember. I have like little readmes sprinkled all over the place for places I normally run FFmpeg to try to remind me of the command I used last time.
Nice, very cool. My tool of the show is Pandas read ODS and read Excel functions. So I know that's kind of really specific. We have talked about Pandas, but it's been probably I think it was 2016 when we talked about
Oh,
Pandas.
wow.
Pandas is basically a library for getting data frames in Python. If you've ever used R, you know what a data frame is. If you haven't, it's basically very similar to an Excel table where you have columns. Each column has a name and a set of values, and then you can do arithmetic. You can add columns together and stuff like that. Um, and Pandas actually can read ODS, which is the Excel file format for the open Excel file format. So you can save a Google Sheet to ODS. Obviously, LibreOffice and OpenOffice read and write ODS. Excel probably will save ODS as well. Pandas can also read Excel files like the XLS and XLSX and all of those files. And what Pandas will do is it will actually evaluate all of the formulas, resolve them to their number. What it won't do is it won't on the fly, evaluate the formulas or anything. That's something that, we talked about at the beginning of the show. But if you have an Excel spreadsheet with a bunch of complicated equations and you want to bring that data, that output into Python, you can just read it in one line using Pandas, which is pretty remarkable. So yeah, I think there's a good synergy there. I was really impressed when I found that function.
That is very cool. The fact that you said it even does like evaluation, not just like reading it as columnar data is pretty cool.
I'm not sure.
About
go ahead.
I was gonna say I want to make a joke about like VB script and whether it evaluates all the random macros, but
oh god, no. I actually don't know if I wonder if the file format saves the function and the value, you know what I mean, in the file, or if Pandas is doing all the calculation. I really don't know.
I will say I've never written a complex enough equation in my spreadsheets that like I would have been able to tell the difference of whether it was like cached or computed, sort of like them. I would like when you open the file, does it take, I guess if you could construct processing complicated enough that it takes literal minutes to sort of finish computing your spreadsheet, in which case it would make sense that they write the value out as well, right? As a cache.
Oh, yeah.
But so it'd be easy enough to test. I've just never written such spreadsheets myself. So,
my guess is it probably has the cached value because otherwise the Pandas people would have to implement whatever library they use would have to implement like every Excel function and test it to make sure you got exactly the same answer.
It's probably one of those things, it's almost non-existent, the number of Excel files with a lot of the very random esoteric functions. So it's how, like, do they support 99% of the files, 5 nines, 6 nines? Like most Excel sheets probably don't even have a formula in them.
Yeah, it's a good point. It's a really good point. But either way, give it a shot. Take it. Pandas is extremely well supported, but still I would always have like a little degree of caution with something like that because you are going from one language to another.
Yeah, there's probably like a decent way to like force it into a good state, even if you have a tail spreadsheet, right? Like copy the values out or something and you lose the formulas, but Pandas would still be able to read it.
Yep. Yeah, totally.
Time for differential equations.
So, we talked about recursive functions scaring new programmers, and now we have something that scares us.
Yes, I'm actually pretty nervous, dude.
I'm shaking right now. So let's start, as we always do, with the motivation. Why people should learn about DiffEq. So, if you usually when you hear about differential equations, you think about physics or maybe economics. Actually, we'll put economics aside for a minute. You think of like physics or these kind of like signal processing, these kind of things that are really kind of low level, things that interact with the real world through sensors and all of that. But there is a reason why a lot of people, even if you're building, a website or something like that, or you're, driving engagement to a website, or you're doing something, you will need differential equations. And that is because of this thing called the law of large numbers. Have you heard of the law of large numbers?
Not in this context. So normally I
Okay.
think of it in statistics. So I'm excited to see if it's the same or not.
It's exactly the same. So the law of large numbers says if you have a lot of things and you need to reduce those things, like let's look at dice. If you say, I want to throw, 17 dice and I want to get the average, right? So, you can just like keep track of all these numbers and take the average and you're going to get something, right? What if you get to like millions of dice or billions of dice? What can you do? What the law of large numbers says is that if I average, a sequence of numbers from a distribution, that average is going to be centered around some point, right? And so, with dice, for example, if you average a lot of die rolls, you'll get something around 3.5, right? If you do it enough times, you're going to get around 3.5. Even if like the first 20 times you rolled, you just coincidentally got a 1, eventually with enough samples, the odds of that kind of anomaly go infinitely close to 0. And so you will end up with a number around 3.5. And so, if you want to do things like how much time are people spending on my website, or how many people a month are visiting my website, or maybe a month's a bad example, how many people a minute are visiting my website. So anything where you're going to end up with many, 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 many samples, you're going to end up probably doing an average, but taking some kind of estimate of these samples, so you're not working with billions of numbers. And as soon as you do that, now you have a continuous number. And so if you were thinking about like traffic coming into Google, right? They're not looking at it in terms of like, okay, I have exactly this many people and then exactly this many people, and I'm going to draw some insights. Like, no, they're taking averages and they're looking at sort of trends over those averages. And they're constructing some type of differential equation that's saying, look, people are, this metric is going up, this metric is going down. Here's the covariance, which means as one metric changes, how it varies the other metrics. And so based on the velocities of these metrics and the covariance of all of these metrics, you can construct a differential equation that shows you like how you think these metrics are going to evolve in the future.
Yeah, so looking at I'm going to start saying words we're not supposed to. Anyways, looking at the rate at which the people are coming out, and then sort of understanding how those change over time.
Yep. Yeah, exactly. And so, there's many situations where you have sort of what you want to achieve in the next time step. And that is easy to compute. I think the balancing stocks was a great example where it's like, if I have 60% stocks and 40% bonds and I want it to be 50-50, well, then I know what I need to do. I need to sell stocks and buy bonds until I hit 50-50. And so, you have your difference, like you have your difference from your goal to your current state. That's relatively easy. What's hard is sort of keeping that stable. So,
yeah. And this is why they pop up in, if you ever read stuff about controls and control systems. So trying to figure out how to turn the steering wheel in your car to get to where you want to go quickly, but not overshoot. And how do you sort of think about computing these things?
Yep. Yeah, exactly. So like, let's say you had, so let's say you like, in this case, it's clear. It's like, okay, there's a percent. And so if I get 1% of one, it's kind of one less percent of the other. Well, let's say you didn't really know that that the stocks and the bonds had to add up to 100%, right? So you might say, well, the stock number is 40%. I need it to be 50%. So, I'll buy 10% more stocks, but then you don't have the exact 10%, so I'll just buy more stocks. But then you buy more stocks and then you overshoot. Or even a better example is you say to yourself, well, my house is 80 degrees. I need it to be 79 degrees. And so, I'm just going to turn the AC on, full blast. But you do that and then it causes you to overshoot. And you have to kind of keep going back and forth. So it turns out that for a lot of these, what you really want is something that is, pretty stable. And another part of this is it gets really complicated when things affect other things. So, for example, let's say you have, air conditioning and humidity. But when you run the air conditioner, it, causes your house to become less humid. And so you might have a humidifier, but then the humidifier drops the temperature. And so these things are affecting each other in this weird kind of feedback loop that can spiral out of control. Like you could end up in a situation where your humidifier is full blast and your air conditioner is also full blast, and they're just going to war with each other because the differential equation is not stable. And if you've ever played a video game with a physics engine, you might have seen this where, if you do something that is unstable, like you try to attach a car to another car and the chain is like not long enough to support both of the cars and everything starts like jittering and then spiraling out of control. That's a case where, the game, because, it wants to run in real time, it's going to take, kind of larger steps and it's going to spiral out of control. So yeah, we should actually talk a little bit about step sizes. So, in Patrick's example of the stocks, right? You might say like buy 10% more stocks. So let's say you instantly do that. And, Patrick is a billionaire, right? So that's not a small transaction. So that's not a small transaction. So 10% of all of that, let's say that influences the stock market, or even just it's happening at a really volatile time where stocks and bonds are going up and down. It's crazy. You buy that 10%, but you buying that kind of changes the market dynamics. Maybe it makes the price go up. And then it also like other crazy things are happening. And so you find that, after I did that buy, I'm actually even further from the goal. It's like being bad at mini golf. You're bad at mini golf, you putt and it goes past the hole, and then you're even further from the hole and you putt again, and it's just getting worse, right? So, one way to do that is to say, well, here's what I'm going to do. I'm going to buy one share of a stock or a bond. Let's say buy one share. It's going to get me a little closer to 50-50. And then I'll measure again. It's like, okay, now I'm at 40.1% stock bonds. So I'll buy one more bond. I'm at 40.2%. I'll buy one more bond. And so you could do that and you'll eventually get equilibrium and it'll be stable, but it will take forever, right? And so that's the paradox, is if you go really slowly, then it takes a ton of either compute or time or what have you. If you go quickly, then you can cause like second order or multi-order effects. And there's an example I have that folks should check out in the fun example section at the bottom. It's predator-prey relationships. And so the idea there is basically, every fox eats one deer, and deer multiply at a certain rate. And the question is, how do you end up with something stable? So if you have 20 foxes and 20 deer and you take one full step, well, what happens? All 20 foxes eat all 20 deer, and then all the foxes die because all the deer are gone, right? So you can't just take one full step or it just destroys itself, right? So you could take baby steps and say, okay, like, again, I'm going to do this. I'm going to assume that because these law of large numbers, that these 20 foxes are actually, 20 million foxes. And so I can kind of divide them into smaller and smaller numbers. And so the 20 foxes start eating more deer, but they don't all eat a whole deer. There's just tiny micro changes, and the deer population starts tanking, and then that means the fox population starts dropping because they start starving, and that allows the deer population to recover, and then you get this sort of like harmonic situation. And basically you can see from this site, like based on the step size, either all foxes eat all deer and then they all die, or you get this like oscillation thing, or with a small enough step size, it kind of converges to some equilibrium where enough foxes are eating just enough deer to match the growth rate of the deer, and it's all kind of exact. And if you had started with that end state, it would be an equilibrium, and you could set the step size to anything and it would just stick there. But because you started from a state that wasn't an equilibrium, the step size really starts to matter. Does that make sense?
Yeah, totally. And I think this is part of the sort of modeling setup and the iterative nature of a lot of these things, and sort of running them forward. And you already kind of mentioning, but simulations, where you hear about this a lot, and thinking about the consequences of what you're doing and how to simulate these things. I think with like what you're saying, I tend to think of a more like discrete way, right? Like, oh, you could have like the foxes be in cells and the deers, I think there were foxes and deers be in other cells, and then like having them move around. And that is one way of doing it. But I guess you call it more like an agent simulation. But that's the only way to do it. You don't actually need to model any individual. This is what you're kind of saying by the law of large numbers. You don't need to actually model any individual deer or any individual predator. Like you could just model it at scale and talk about the full thing, where doing an agent-based simulation actually would run into a lot of problems. So they're sort of treating the problem with different approaches.
Yep. Yeah, exactly. And so, a lot of biologists, I mean, definitely biologists in like the 1900 or 1800s and stuff, they couldn't do the simulation. And so they had to rely on these really coarse things where they'd have people go out and like, count the number of foxes in like a whole county, and then do that a few times until they can get some kind of statistical average. They could use the law of large numbers even if they don't have a lot of numbers, right? And so just tolerate some kind of error there, and then move into differential equations. So yeah, so I think okay, yeah. So we'll dive into you'll hear the word ordinary differential equations and partial differential equations. So if you look at like the fox example, the number of foxes is affected by the number of deers and vice versa and all of that. But you don't really care about modeling it in those dimensions. The only dimension you really care about is time. So it's like, what is going to happen in the future? So, if F is the number of foxes, D is the number of deer, and time is T, T is the only one you're exploring. Now, F and D are changing as you move through time, but you're not moving through the number of foxes. You set an initial value and then you move through time. And so what that means is you're only differentiating through time. So that's where partial differential equation comes from. The equation has many different variables, but you're only interested in a part of them for the purpose of differentiating. And so if you're only differentiating through one variable, and there's maybe some other conditions too, then you have an ordinary differential equation. And if you have an ODE, then a whole bunch of techniques open up to you. Another thing about, I think, ordinary differential equation is there's no discontinuities. So this is again a really point that folks can get stuck on, right? They might say, well, I might have some if statement that says, well, like if I'm in a certain case, then the foxes eat the deer. Otherwise, the foxes don't eat the deer. And so there's this break, right? There's some variable that's like binary, right? And if you do that, then all of these techniques aren't going to work. And so that might sound really limiting, but again, when you start looking at really large numbers, you should kind of expect everything to have some inertia, right? You shouldn't expect there to be like these really sharp discontinuities, just like, you wouldn't expect like everyone to leave Google tomorrow. Like it's just not really reasonable. Like even if Google like somehow the whole page is full of ads tomorrow or something, they made some kind of really bad product decision, there'd still be like this decay, right? So at this scale, a lot of those constraints are pretty manageable. And so once you have an ordinary differential equation, then there's a whole bunch of interesting things that pop up. In the way that we were talking about solving, Patrick's stock balancing issue, we were using Euler's method. We were basically saying, we know how to get exactly to the goal, but we know that if we took that big step, that it would cause some disruption and it would move the goalpost, and we would be in trouble. So we'll take baby steps, and at each step, we'll reevaluate the distance to the goal. This is another good example of this is like missile tracking. So if there's a target and you have a missile might, like you're playing some kind of video game or something, the missile might say like, oh, my target's here. I need to draw like this arrow, like I need to go in this direction. But then, the target's moving. So as the missile is going to the target's also moving. And so, the missile would end up kind of curving towards it if it didn't have any predictive capability, right? And so that's another example of a differential equation. So Euler is a first order method. There's also like second, third, fourth order methods. And what these do is they look at a series of predictions and they use a series of these to get an even more accurate step. So for example, this is using the mini golf example. Let's say you overshot the hole and you kind of learn to yourself like, okay, I need to hit it a little less hard next time, right? So even though like maybe you overshot the hole and you're twice as far as you were last time, you kind of learned, okay, I need to hit it twice as hard, but also a little bit less because I clearly hit it too hard this time. So let's say you hit it and you hit it, 1.5 times as hard and you still overshot the hole. So you kind of learned like, okay, I need to hit it even less than that. And so with these other multi-order methods, you can take bigger steps towards the goal and still have less of this overshooting problem because it's taking more information into account.
We were been talking about, I guess, like controls and like controlling things or taking action. But I think we also see them pop up in sort of running physics engines and games. And to me, it's a little different. You're attempting to model the setup of the differential equations, like the force of gravity on a ball falling down in your video game. And there, you're trying to say, I'm actually wanting to compute position by given an arbitrary time. So I'm going to give you some time in the future, which is, my game last displayed here, and I've moved X time step forward, and setting up your equation so that instead of defining that step in advance, you can compute the position at an arbitrary time into the future. And so there, I think to your point, you're sort of changing the situation a bit. Rather than what action am I going to take, you're sort of giving the system, hey, here's a new time. Can you tell me what all the positions are now?
Yeah, that makes sense. Yeah, actually, it's a really good example. Like, imagine if you have a ball that's moving towards a wall. You might say to yourself, well, like, this is a pretty simple situation, and I could take a pretty big step. In fact, if there's nothing around, maybe I take such a big step that the ball hits the wall, and I don't have to think about anything in between. So just maybe the ball is so far from any other object that you just say, look, for the next 3 seconds, this ball is going to arc and it's going to bounce off the wall, and I can come back 3 seconds later. I don't have to do any math at all. Conversely, like maybe the ball is chained to another ball, and both of those balls are now like, moving through the air, but in weird ways where they're kind of pulling on each other, right? Well, that is really unstable, and so you might need a really low time step. And all of these physics engines do kind of dynamic time stepping and stuff like that. But using a multi-order method is even better if you can afford it. So the equations are more complicated.
I thought you said two things. I thought you were going to do three, and we were going to talk about the three-body problem. But no, you avoided that. But I mean, just to reference that, I mean, I think one of the things you'll see pop up when you're talking about differential equations is if you think about, as Jason was mentioning, things interact with each other. So it's not just one object moving through the world without consequences. If you think about in space, if you think about two planets or two massive objects or low mass, anyways, it doesn't matter. Think about two things in space near each other, they are pulling on each other gravitationally. There's a force, right? So this is like you are trying to understand, why does the moon orbit the Earth, but the Earth, moon together also orbit the sun? And so if you sort of think about the interactions of these as they play out and fast forwarding through and understanding where they're going to be at some time point, it depending on the level of precision you care about, the moon is way smaller than the Earth, but it does actually cause the Earth's orbit to wobble around as it spins around. It's pulling on Earth just as Earth is pulling on it, which is, you'll see things like, oh, we are predicting that there's a planet that we can't see because there's these slight disturbances in another orbit of a planet, as something is passing by, and they pull on each other. And, that it's sort of a continuous thing. And it doesn't matter how small or big it is. Now, at some point, you probably just don't care about it anymore, right? A baseball, space debris floating around the Earth has an influence on its orbit, but it's at such a degree you're probably going to ignore. But as you sort of try to account for more and more of these at increasing levels of precision, imagine trying to launch a space vehicle to meet up with Mars and make a precision landing, right? You need to be able to solve these differential equations in a very precise manner. And as Jason's pointing out, like allowing to layer on more and more, ways of increasing the accuracy and precision, because you really care. You really want to know the exact moment that the two things are going to meet up, because it has a range of consequences, including how much fuel you put on your rocket, and how much fuel you put on your rocket determines how much velocity it's going to have. And it's a cascade of things, and you need a setup that allows you to iteratively converge on a solution.
Yeah, totally. I mean, there's so many things where when you start modeling at a high level, you run headfirst into differential equations. Like imagine you're making some kind of strategy game, right? So it might be that if you want to know if your game is fair, if it's balanced, it might be hard to do that in simulation, because you have all the different units and they're moving around, and it could be really difficult to think about all of that and compute all of that. What you could do instead is, come up with some mathematical models that say, okay, if I have, so maybe I have a measure of army strength, which is just a number that I've learned. And I've learned that, for this configuration of units, I have a strength of this. For this configuration of units, I have a strength of that. And I learned some function that says, given two army strengths, which one wins, and maybe what's left of their army after they win. So given two army strengths that fight, what are the army strengths at the end? One of them will be 0 and the other one will be something. Now you can construct sort of differential equations that talk about, should I, if I like what happens to my army strength as a function of the current base? Am I like, how is the army strength growing and subtracting and all of that? And so, once you start abstracting out to kind of a higher level, then you start running into differential equations. So if you ever play like SimCity or Rise of Industry or these type of simulation games, they're going to be full of partial differential equations. And I bet you even beyond what's in the game, they were tuned, and that game was tuned using differential equations solvers. Another like more kind of industrial example or commercial example is PageRank. So PageRank was the algorithm that Google used initially to rank all the content on the internet. And the way it works is they manually give some amount of rank. Think of rank as like a resource, right? They give some amount of rank to a bunch of websites that they code up by hand. And then they say, when those websites link to a website, some of that rank is diffused onto that website. So, if you know, like MSN.com links to some Kotaku.com, and some energy passes from one to the other. And so initially they used Euler's method. So they said, well, we're not going to give just all of MSN's energy to like the first link we see. That would be crazy. So we're going to look at like roughly how many how many domains does this domain link to, and we'll diffuse some portion of their energy equally to all of those pages. And they're linking to other pages, and those pages are linking to other pages. And so you have this multi-order effect. And so you have a partial differential equation. So as time progresses, this rank diffuses through all of these websites until eventually it stabilizes. And using differential equations and the theory behind that, you can compute the page rank more or less efficiently while still getting a pretty stable answer. And even when you're trying to figure out how much rank should I diffuse among the different pages, and what's the most fair way to do that, differential equations will allow you to do that very quickly. So, for example, if you were to just use Euler's method and compute page rank on the whole internet, maybe that would take days, maybe months. But if you were to use faster methods, you could get the same answer in like 2 minutes. And so getting it that quickly allows you to do a lot more interesting analysis.
We haven't yet told people how to actually solve differential equations, Jason.
Oh, man. That's a really good point.
I'm teasing. I think this has been a great sampler, like an overlook of the various aspects. And I feel like it's one of those things where, hearing it over audio, I guess maybe some people are out there furiously scribbling notes. But I feel like that's the right way to cover it, to give sort of the list of things, the sort of what's the next hop in the journey to learn more about these things, to understand if you've encountered these things and didn't know the right words for it. We were talking about that, right? About, Wikipedia versus ChatGPT. Like, how do you sort of find the next thing? So I hopefully this has been useful to people. I mean, without going into a very lengthy discussion about how to actually run Euler's method or do some of these things, I feel like this has been a great introduction to the topic.
Yeah, I think this is one of those categories where you should use software off the internet. So scipy, like scipy for Python is amazing. They have like 7 different solvers. They're all great. But I would say the first thing you need to do is come up with a function, and you can pick whatever language you want, but come up with a function that says, given my variables, so like using Patrick's example, given my percentage of stocks and bonds, what is the step, like what is the difference I need to make to solve that? So in Patrick's case, if he has 40% one, 60% the other, then the difference is to get it to 50-50. And I guess, you need the denominator for that. But let's say you pass that in. It's like, okay, here's what I could do that would like instantly solve my problem based on what I know right now. Come up with that function. Make sure it doesn't have any side effects. Doesn't need to like read from a file or anything. It's some pretty small function. And it doesn't use globals or anything like that. And then you can plug it into a solver, and you can actually explore different solvers and see what happens. Cool.
Very cool.
Yeah, definitely check it out. It's an important thing. You'll often be in a situation where you know what needs to be done, but then you do it, and as you do it, you change the nature of the system, and it seems like you never really get to the goal. That's what differential equations are really good at fixing. So, yeah, check it out. Check out the links. We have a ton of really good content in the show notes. You can go to programmingthrowdown.com, or you can look at the show notes tab of your podcast app if you have that available. You can also go on our Patreon, and we have all the show notes there and a super fast RSS connection over there.
Thank you, everyone.
Yeah. All right. Thanks, everybody. My head hurts. How do you feel? Is your brain on fire right now?
I guess it's time for me to compute the rate of change of hormones in my brain from neural connections.
I need to compute how hard my head hits the pillow.
Oh, no.
All right, everybody. Hopefully we didn't melt brains. It's a super interesting topic, and we will catch you all next time. See you later.
Music by Eric Barndollar.
Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.